Welcome to the theory of regression discontinuity design. This is some supplemental material that I put together from a variety of sources, including my colleague Scott Cunningham's new book, Causal Inference, the Mixtape, and other sources that I was able to glean off the internet, including the most recent Nobel Prize winner, Hito Imbens. So the first thing that I wanted to consider when thinking about regression discontinuity design is establishing whether anything unusual happens because we have an explanatory variable that's binary. So if we consider a model where k is 3, so I have an intercept, I have a conventional continuous explanatory variable, and an additional explanatory variable that is binary. And in the notation here, you can see that that additional variable is denoted as d for the dummy variable, which is either 0 or 1. The interpretation of the regression would be that the intercept, as before, is beta 1, but what beta 3 provides now is, in essence, an intercept adjustment, so that when the dummy variable is 1, the intercept for this subgroup is now beta 1 plus beta 3, whereas when the dummy variable is 0, the intercept remains beta 1 as before. So we have parallel lines and an intercept shift that's estimated by beta 3. Then if we want to consider the mathematics of estimation and establish whether anything unusual happens, we start with Verbeek's notation for B3, which is the estimated coefficient for the explanatory variable that's binary. And just so you remember, when Verbeek, what Verbeek denotes as M sub Y3, that would be the sample covariance between the dependent variable y and x3, which in this case is the dummy variable d. So I took on the right-hand side Verbeek's notation for the OLS estimator, and then I expanded it out in the second row. I expanded the numerator from the M notation into conventional deviation or conventional notation of yi minus y bar, di minus d bar, just so we can see more carefully what's going on when we do this. So what I would remind you, a couple expansions. So the first expansion, you remember, as always, when we have a computation like this, what we want to do is substitute for the dependent variable y its population regression function definition. So yi is equal to beta 1 plus beta 2 xi plus beta 3 di plus the stochastic disturbance term epsilon I. And then y bar, the sample the sample mean would be beta 1 plus beta 2x bar plus beta 3 d bar plus epsilon bar. And then finally, when I take the expectation of those terms, the expectation of every epsilon is 0. So this means that the epsilon term goes away, as well as epsilon bar. And then I have beta 1 added in and subtracted out. So what remains when I take the expectation of yi minus y bar is this term of beta 2 times xi minus x bar plus beta 3 times di minus d bar. So if I substitute that, so if I now take the expectation of beta 3 and I put that last line substituted into the right-hand side of beta 3, I get this expression that's here. And what I've done for the purposes, since this is just such a long computation, I had to break this into two separate lines. What I did is I broke it at the minus sign. You notice from the second line, I have an expression, a continuous multiplicative expression, and then I subtract a second multiplicative expression. So I have separated those two additive expressions into separate lines now in this last one, and they're of course over a common denominator. So at this point it's just substitution. Then I felt comfortable at this point to go back to M notation just to make this a little less verbose, and I kept it in two lines so you could verify how all the terms that are in the first line or the first line of the expanded expression now map into the first line of this final expression. The second line of the more verbose expression maps into the second line of the expression in M's given here. Now you can see at this point everything. So the first term, beta 2 M23 times M22 over the denominator, appears in the first line, and with a minus sign, the same exact expression in the second line. So what happens then, of course, is that all the terms with beta 2 cancel out, and I'm left with terms that have beta 3 alone. So when I consolidate those terms together, what I find is beta 3 is multiplied by the same expression that's in the denominator. So since the same expression is in both numerator and denominator, it cancels out, and we have that the expectation of B3 is beta 3. The reason why this is important is we've now shown that when my second explanatory variable is binary, nothing unusual happens to the mathematics. The standard consistency calculation that we've done before works just as well with a binary dependent variable as it did with a continuous explanatory variable. So we're good to go. So now we apply this to the regression discontinuity design. And the way we could describe the regression discontinuity design, it's a specialized application of a binary explanatory variable. So in the textbook up to this point, we've considered we've considered models in which we have a binary explanatory variable, but what we're trying to establish in this slide is when can we say that that this is in fact causal. Okay, so it is causal if we have an exogenous event which happens that changes the expected value of y conditional upon x. You remember the word exogenous, what this means is it's determined outside the system. So some completely different process determines the status of the treatment variable, then determines the outcome. So a few examples that I would argue are exogenous events, events that determine outside the system, which affect or which change the conditional mean of y. So the first one that we're going to spend a lot more time on, a student becomes 21 years old and can legally drink alcohol. So this is the basis of the paper that we're going to cover next, which was the paper that my co-authors and I did on what happens to the GPA of cadets at the Air Force Academy when they turn 21. I won't spoil it, but it's a very amusing paper. So, God causes people to turn 21 years old. There's nothing that you can do to manipulate your 21st birthday to make it come sooner or later. So it is an honest-to-goodness exogenous event, and And in this case, I would argue that turning 21 and having legal access to alcohol did change the expected average GPA of the cadets whose data we had. So second example, a person becomes 65 years old and becomes eligible for Medicare. You might remember from other classes that you've taken, particularly if you took my Economics of Government class, Medicare is the program that offered by the federal government that provides health insurance for older Americans. And the eligibility criteria is, are you 65 years old? So we have the exact same story at the other bookend of life, right? When you become 65 years old, you are eligible for Medicare. And that would change your eligibility for Medicare provided health insurance. Another example that we make use of in 5347, I have this data set looking at 30 years worth of officers and enlisted personnel in the U.S. military. And back in 1986, the federal government passed legislation which, if you had your first commitment or contact with the military after August 1st, 1986, then your retirement benefits were cut by 20%, right? So the standard military retirement package is after 20 years of service, you are eligible for your final base pay, a pension of your final base pay, 50% of your last paycheck, 50% of the average of 3 years over your last final pay, but you receive 50% of your pay for the rest of your life. And this legislation was passed that cut it to 40% for people who had their first contact with the military after August 1st, 1986. It was later repealed, but another co-author and I attempted to study the effect of people's willingness to remain in the military after this cut in retirement benefits happened. Okay, so these are all exogenous events that are determined outside the system. What is necessary for this to be considered causal? So what I mean by a causal interpretation, it's almost an antiseptic experimental type interpretation, right? So if we have an honest-to-goodness causal effect, what that means is if we drew a person at random from the population and applied the treatment to them, we are estimating how that treatment would affect their outcome of interest. Okay, so regressions in a conventional sense, in the old-fashioned sense, estimate correlations. I often begin the econometrics course by saying that what simple ordinary least squares regression literally does is it says when my explanatory variable is above its mean, do we see the dependent variable, generally speaking, above its mean or below its mean? And at a most basic level, that is what regression does. It's looking at correlations, right? So when the explanatory variable is above its mean, generally speaking, is y above its mean or below its mean? The causal effect, by contrast, estimates something that's not a correlation but an actual causation, meaning that if I were to apply the treatment, this is how it would change the outcome for this particular economic agent. So the absolute necessary conditions are that the agent cannot self-select into or out of treatment. It should be relatively obvious why this is a necessary condition. Consider what would happen if the agent were able to determine whether they were in the treatment group or the control group, right? They would then be able to, in essence, manipulate the outcome. and observed differences in outcome between the treatment and control group could not necessarily be attributed to the treatment. Some degree of that outcome might be determined by the actions of the agent, which would then pollute our ability to interpret this as causal. The other condition is the other explanatory variables which affect the outcome vary continuously when the treatment is applied. So if we go back to the Air Force Academy drinking paper, if our thought experiment is we're in essence comparing the GPAs of students who turn 21 right before final exams versus those who turn 21 right after final exams. For this to be an honest-to-goodness causal estimate, it's necessary that everything else that might affect students' grades vary continuously through their 21st birthday. So prior coursework taken, their SAT math score, their effort, all these other things have to vary continuously. And the only thing that changes fundamentally is turning 21 and having legal access to alcohol. If that is true, then we can argue that this is a causal estimate. Okay. So, speaking of selection, wanted to present these possible scenarios to you and ask you to think whether we have any potentially problematic selection issues. So I've already kind of made the case that that the first example is free of potential selection into or out of treatment. So treatment is legal access to alcohol. Legal access to alcohol occurs when you turn 21 years old, and there's nothing that you can do to accelerate your 21st birthday or delay it, right? You turn 21 when God intends for you to turn 21, and that's the end of the story. So the second one, eligibility for SNAP, the Supplemental Nutritional Assistance Program. And the criterion for eligibility to SNAP, I believe currently, is that if a household has, it's a multiple of the poverty level income. So I believe it's twice, could be wrong about that. But there is a cutoff, an income cutoff. If your income is above the cutoff, then you're ineligible to receive SNAP benefits. If the household income is below the cutoff, then a person is eligible for SNAP benefits. I would argue that this one is subject to manipulation, because if a person's income was just a little itty-bitty bit above the cutoff, so they're ineligible to receive SNAP benefits, it would be possible for a wage earner to cut back their hours just a little bit to drop household income and become eligible for SNAP. So this second example, I would argue, is subject to manipulation. Okay. So the third example was the military example that we've talked about. This one is a little bit, well, I would argue that by and large, people make their, people don't necessarily think about retirement benefits when they make their first contact or sign the dotted line to enter military service. But it is possible, if we really want to spin a wild and crazy story, if in June or early July 1986, someone went to their Air Force recruiter and said, you know, I'm thinking about joining the military, and the recruiter told them, look, if you sign the dotted line before July 31st, your benefits, your retirement benefits, if you decide to become a career military officer, are going to be 20% higher. It might be possible for a small group of forward-thinking people who are informed of this change to then sign, if they were wavering, whether to sign in late July or early August. it is possible that there might be a small number of people right around this cutoff date that could accelerate their commitment and then, in essence, be in the control group, the group that was eligible for higher military benefits. So that one is, there might be a small group that could manipulate their treatment status. But as you move farther away from July 31st, 1986, I would argue that there probably isn't too much manipulation, but there might be some. So the next one, Congress passes legislation raising taxes on capital gains realized after January 1st of the next calendar year. This is a classic. And I would argue that if someone had large amounts of unrealized capital gains and they knew that the tax rate on those capital gains was going to go up after January 1st, the temptation would be very great to realize the capital gains in the previous tax year and then subject them to lower taxation rates. Right? So this particular example, I would argue, is absolutely rife with self-selection. Right? There's great opportunity for investors to select which tax rate their capital gain is subject to. Okay. Colorado announces the state minimum wage will rise 6 months in the future. So if it's well known that the minimum wage would increase, is it possible that, well, I guess to spin a story, what if McDonald's, a fast food restaurant such as McDonald's, was building a new restaurant and they had knowledge that the state minimum wage was going to rise? Is it possible that in the construction of the restaurant, this might affect the decision of how many self-service kiosks to put in? Right? So if in the process of building the restaurant, more self-service kiosks were installed, then that would be less employees subject to the higher state minimum wage. It's possible, right? Okay, it is necessary and critical that the only thing which changes at the time of treatment is the treatment itself. And we've talked about this a little bit so far. So the classic clean example, again, would be the drinking example at the Air Force Academy. We have to argue, and we'll show evidence when we go through the paper in the next lecture. I will show you how we attempted to justify that there was no variation in any other measurable explanatory variable through the discontinuity, through the 21st birthday. So if we want to put on our theoretical hats for a moment, the framework, the theoretical framework that's used for identifying causal frameworks and causal effects is what's called the potential outcomes framework. And the way to think of it is that we would like to ideally compare the outcome of an individual who receives treatment with their outcome should that same person not receive treatment. And the typical language of causal inference, this is called the counterfactual, right? So if we think again to the Air Force Academy, if someone becomes 21 and is eligible to drink, and they go and they drink a lot the night before their final exam, we would want to ideally compare that person's academic performance with that very same person in an alternate universe where they didn't have access to alcohol. And of course, the problem is we can only observe one state of the world. The other one basically has to be estimated statistically, right? This is basically what we're going to have to do. Now, using Verbeek's notation set, from section 7.7, we will define y sub 1i as individual i's outcome in the post-treatment period, and y sub 0i as individual i's outcome in the pre-treatment period. So the first subscript there, the binary 0 or 1, indicates whether this person has been treated or not. Okay? And then let the treatment variable d be defined as 1 if the treatment is applied to subject I, and 0 if it is not. What we can say then, going to the lines at the bottom of this slide, y sub 0i given d sub I is equal to 0, that is subject I's outcome in the pre-treatment period given treatment has not been applied to them. Okay? The second term, y sub 1i given d sub I is equal to 1, that is individual i's outcome in the post-treatment period given treatment has been applied to them. These two states of the world on the first line are both observed, right? When in the pre-treatment state of the world, treatment has not been applied, and in the post-treatment world, treatment has been applied. The other two expressions at the last line of this slide are counterfactual and not observed. So the first one, the way we'd interpret that is subject I's outcome in the pre-treatment world given they have been treated. Okay. And the second one, or the fourth one, the last one, is subject I's outcome in the post-treatment world given they are untreated. So these two states of the world are unobserved. They're counterfactual. They did not happen. And to estimate the treatment effect, we have to make heroic assumptions about these and statistically estimate them. Right? So the average treatment effect is estimated as the average outcome in the post-treatment world minus the average outcome in the pre-treatment world. But for this to be causal, it must be that the expected value of subject I's outcome in the post-treatment world, given they have not been treated, is the same as their pre-treatment outcome given they have not been treated. And this is known in the causal inference literature as the continuity assumption. And it's not directly testable because the counterfactual state of the world is not observed. It can be informally checked by ensuring that there are no other explanatory variables that have a discontinuity at the time of treatment. And we've talked about that. So to estimate a regression discontinuity design, we have the model where we have one continuous explanatory variable and a binary explanatory variable, which will be the treatment status. Right? Is treatment applied to subject I or not? Okay. So the way we could think about this is this would be a well-defined causal model if this counterfactual state of the world, which I indicate with the dashed line, if there are no additional discontinuities. So, for instance, what I show in this particular chart is that x, the continuous explanatory variable, does not have an additional discontinuity at the time of treatment. Right? When treatment is applied, x is varying continuously through the discontinuity point. Okay. A direct application of the continuity assumption, which I repeated here, remember this was that the expected outcome varies continuously between the unobserved counterfactual status and the observed pre-treatment status implies that the estimated average treatment effect is the average outcome in the post-treatment period minus the average outcome in the pre-treatment period. It should be estimated using a sample comprising only observations within a very narrow window on either side of the discontinuity. So immediately before and immediately after the discontinuity. So for instance, if we go back to this previous slide, you can see that if I compared the outcomes of, so in this slide, the Greek letter tau along the horizontal axis is when the treatment effect is applied. What this slide is saying is that ideally what we would like to do is compare people just before tau with people just after tau, because those will be most directly comparable. If we went farther to the left, you can see that values of x might be different than values of x at the far right of this diagram. So as we move farther and farther from the treatment, the time of treatment, the direct comparison is not so easily made. So thinking about our Air Force Academy drinking experiment, what this says is ideally we would like to compare people who turn 21 within a couple days of final exams versus those who turn 21 within a couple days after final exams. This would be the ideal situation. This would be what in the causal inference literature is called a short estimation window. The virtues of a short estimation window is we don't require additional explanatory variables to ensure direct comparability. We can literally compare the average GPA of people who turn 21 right before final exams with those who turn 21 right after final exams, and we don't need any more explanatory variables because these two groups are directly comparable. The flip side of it, the bad aspect of this is if we look just at the people who turn 21 within a week before final exams versus those who turn 21 a week after final exams, we're talking about a really small sample size. And you, of course, recall that when we have small sample sizes, that reduces the precision of all statistical estimates. So we have reduced precision in estimating the post-treatment outcome and the pre-treatment outcome. So our other option is what we would call a long estimation window. So we include people maybe 6 months prior to, so from 6 months until right before final exams. So did they turn 21 within the 6 months prior of final exams versus those who turn 21 within 6 months after the final exam. The problem with this is we might have a harder time justifying that the continuity assumption is met, and we may need additional explanatory variables to ensure more direct comparability between these two groups. Right? And finally, it may be necessary to do this if the outcome is noisy. So if there's a lot of stochastic variation, we might just simply need a longer estimation window to estimate differences between y sub 1 bar and y sub 0 bar. And in essence, we had to do that with the Air Force Academy experiment. It just simply, grading outcomes, grades are noisy enough, we weren't able to precisely estimate outcomes for the narrow window we would have really liked to. It just didn't happen. So A typical statistical control is to have some sort of some sort of trend before versus after. So again, thinking about the Air Force Academy experiment, there are linear trends in grades. So well, it's probably a bad story, but cadets are notorious for becoming infected with senioritis. So as they get closer and closer to graduation date, their effort falls off. I can tell you stories, but won't right now. Ask me later, I'll tell you the story. So there is a gradual downward trend in earned GPA as cadets become older and as they become more severely infected with senioritis. So it's necessary to have a linear trend or some sort of trend in the data. And one of the questions in the causal inference literature is, should we just estimate these trends with a linear specification, or should we do quadratic? And you can see the illustrations here that I have in this slide. The virtue of higher order polynomials is that they can estimate more flexible effects, but it is possible that a quadratic trend could absorb, it's more likely to absorb some of the discontinuity itself. So because of this, quadratic trends have fallen out of favor in the literature. Our drinking paper went to print in 2011, so a little more than 10 years ago. And I recall at the time, the editor was pressuring us to include a quadratic trend. And the quadratic trend specifications, which we don't actually show in the paper, as I recall, were somewhat problematic. I think we just put a footnote saying that they were largely similar. But the linear trend was much cleaner and more carefully identified. So the other major variation in regression discontinuity designs is in what the literature calls a sharp regression discontinuity versus a fuzzy one. So the examples that we've talked about so far are sharp regression discontinuities. The reason why they're called sharp is that at the point of treatment, the probability of a subject being treated changes from 0 to 1 at the time of the treatment. And after the time of treatment, being treated is a certainty. So, as an example, let the treatment of interest be enrollment in Medicare. You recall that Medicare is health insurance for old people. Prior to becoming 65 years of age, enrollment in Medicare is almost universally disallowed. There are two notable exceptions. End-stage renal failure, so that's kidney disease, people who need dialysis right before either a transplant or death, and then ALS, which is also known as Lou Gehrig's disease. So those two diseases, if people acquire those before the age of 65, they are eligible to enroll in Medicare. But once a person becomes 65, eligibility to enroll is universal. So this would be an example of a sharp regression discontinuity. A fuzzy RDD, in contrast, there is a discontinuity, but it's not a discontinuity in treatment from 0 to 1. So in other words, we have some subjects being treated before the discontinuity, and after the discontinuity, not everyone is treated. So as an example, what if the treatment of interest that we were thinking about was admission to Baylor? And suppose that the admissions office at Baylor has a sharp, bad word. There is a discontinuity in the probability of admission around the SAT, a combined SAT score of 1200. So what we would say then is that there are some students who are admitted to Baylor with an SAT score of less than 1200, but once the 1200 threshold is crossed, the probability of being admitted to Baylor goes fairly sharply up. It's still not universal, but there is a big jump in the probability of being admitted to Baylor as the SAT score crosses from just under 1200 to just over 1200. So this would be an example of a fuzzy regression discontinuity. Okay. And just to give you a little math, the estimated treatment effect, suppose it occurs when the explanatory variable assumes the value x sub 0. So if we borrow the example from the previous slide, this would be, so x would be the SAT score, x sub 0, the discontinuity of interest would be at an SAT score of 1200. So this estimated treatment effect, what we're doing is we're taking the limit in the expected probability of admission as we have the SAT score. So in the numerator, first term, we're taking the limit of the expected probability of admission as the SAT approaches 1200 from below minus the probability of admission as the SAT score approaches 1200 from above. So we're looking at this discontinuous change in the probability of admission as we approach the point of discontinuity in SAT scores. And then in the denominator, we do the same thing. We're taking the limit. Well, we're taking the expected probability of admission to Baylor as SAT score approaches 1200 from below minus the expected probability of admission as we approach from above. Oh, you know what I should have said, I guess to maybe clean that up a little bit. Y would be the outcome of interest. D is the treatment effect. So the treatment effect is whether someone enrolls in Baylor or not. Perhaps the outcome of interest that we might study would be salary at age 25, right? So we're looking at the difference in salary of 25-year-olds around this discontinuity of SAT score of 1200, given we have this discontinuous change in the probability of admission. Okay. So mathematically, a fuzzy regression discontinuity design contains two equations, one to determine the treatment status. So in this case, are they admitted to Baylor or not? And the second to estimate the treatment effect. So it would be the effect of a Baylor degree upon salary at age 25. The fuzzy regression discontinuity system must be estimated by two-stage least squares, which we're going to cover in Verbeek Chapter 5. So stay tuned, we'll get there, but wanted to just show this to you given we're talking today about regression discontinuity designs. So the threats to identification in a fuzzy regression discontinuity, it can be complicated if the assignment rule is known in advance. So if someone really wanted to go to Baylor and they knew about this discontinuity, that might affect their willingness to pay for SAT tutoring to try to cross this threshold, right, and increase the likelihood of treatment. If agents are aware that they can gain by manipulating their treatment status. So if the rule is known, if subjects knew that a Baylor degree would substantially increase their income, that would affect their willingness to then pursue activities that would increase the likelihood of treatment. And agents have the time and/or ability to adjust in response. So one of the things that that Professor Cunningham mentioned in his causal inference book is one way to check for this is checking for uniformity of density in a neighborhood around the discontinuity. So if nationwide SAT scores varied continuously through 1200, what we could do then is look if there's piling up just over the threshold of people who Baylor applicants who turn in SAT scores of just a little itty bitty bit above 1200. So anyway, that is regression discontinuity designs. It's a very popular technique. You can see that the econometrics of it are really quite simple. The work in claiming that this is a causal effect is theoretical, right? Is the design of how the data was generated clean enough to be able to argue in such a way as to be credible that the effects really are causal?